So we're going to start with trapezoid rule. And in order to use trapezoid rule, it's helpful to know the area of a trapezoid. Area of a trapezoid is 1/2 times the height of the trapezoid times the sum of the bases. That's just geometry. In our context, the height of the trapezoid is actually going to be the width. It's the same width you've always done, b minus a over n. And I'll show you visually why that is in just a minute. But we're going to jump right in with an example, and then I'll walk you through how to do it with the example. So we're going to estimate the area bounded by the function f of x equals 6x minus x squared and the x-axis using 6 trapezoids.
Whoa. Wait up.
I will wait up.
So basically the area formula is the one for a triangle, but just
The one for a trapezoid.
the only difference is you have to add the bases because it's more than one.
That's correct. And triangles and trapezoids are actually very closely related, and it's very astute of you to make that connection, because I was going to make that connection in a few minutes.
You should say it louder so the camera can hear.
Do you know my first period said, several students said that they have never met you, but they feel like they know you from watching the videos.
Aww.
Yep.
Dangerous students. So
Yep.
sweet of them.
I know.
I appreciate a first period.
Okay. One of the problems, the dilemmas of this example is what did they not give us? Say I asked you to find the width.
Range.
They didn't give us the left and right endpoints, right? They didn't give us lower and upper bounds. So when they don't give you limits for your function, you're going to have to find them yourself. This is an upside down parabola, which means we need to figure out where it intersects with the x-axis. So all we have to do is set our function equal to 0.
Add x squared to both sides, or not?
No, when we solve it quadratically, I always set it equal to 0, and then what do we do? We factor. But it was a good try.
Bad algebra.
Right? Okay. So we factor out an x. And what are our two zeros?
0 and 6.
0 and 6.
It'll work out the same.
So our left endpoint is 0, our right endpoint is 6. Our width is 6 minus 0 over 6. Isn't that lovely? They gave us a width of 1. Okay, let's draw a picture of what's going on. So we have an upside down parabola, goes from 0 to 6. One, two, three, four, 5. So we're splitting it into 6 trapezoids. How do you draw a trapezoid? With a rectangle, you get some sort of a height and you level off the top and create a rectangle. Trapezoids, you don't level off the top. You actually connect these two y values together, and that's the top of your trapezoid. So these are actually, if you think of a traditional trapezoid, right? A trapezoid, by the one definition, is any quadrilateral with one pair of parallel sides, right? So our trapezoids are actually like this, where we actually have right angles here and here, and we just have one slanty side, right? And it's turned sideways. Okay? Can you guys see how these are trapezoids? Okay. So these are trapezoids just turned sideways. So that's why the height, normally this is the height of the trapezoid. The height of the trapezoid is actually the width. Okay? Okay. So our area, let's make our table. Start at your left endpoint and walk by widths. And we get the y values just by plugging into our function, 6x minus x squared. So when x is 0, we get 0. If x is 1, we get 5. If x is 2, we get 8. At 3, we're at 9. And then it's symmetric, we get 8, 5, 0. So our area using trapezoids is approximately. Don't forget, the trapezoid formula is 1/2 times the height, which in our case is the width, which is 1 times. It's the area of each trapezoid. Well, each trapezoid, you do 1/2 times the height times the sum of the bases. So for the first trapezoid, the bases are 0 and 5. So for our first trapezoid, we'd have 0 plus 5. For the next trapezoid, the bases would be 5 and 8. If you look, each trapezoid shares a side, so this one and this one, they share this side. So use that, each side you're going to use twice, one as a left side and one as a right side. So we'd have 5 plus 8. And then you move over to the next pair, 8 plus 9. And the next pair is 9 plus 8. And then 8 plus 5. And 5 plus 0.
Do you have to do that smaller trapezoid by area or no?
No, I was just writing, hey, this is the area using trapezoid rule, but let's move this over. All right, and then you would put that in your calculator and get the answer. And I think I can tell you because I've got it written down. And the area is 35. So that's trapezoids. So for rectangles, you just do width times height, 1 height for each rectangle. For trapezoids, you do 1/2 times the width times the sum of the height. So you're going to have 2 numbers for each trapezoid. The ones, every number gets used twice except the ones in the ends. And one thing I wanted to point out is if you look carefully, the shapes on the ends here aren't actually trapezoids, they're triangles, right? But if you look at your formula and you cover up one of the bases, right, you have 1/2 base times height. A triangle is really just a trapezoid where one of the bases is 0, right, like 0. So they're very closely related. So you can still use trapezoid rule when you have triangles. Just one of the bases is 0. All right, that's all we're going to do with that. It's time to move into the fun stuff. Here comes the meat.
Can you do trapezoid rule by just adding upper and lower? Didn't you say that yesterday or no? And then like dividing it by 2.
Yes, I think you can. I'd have to, yes, yeah,
Okay.
you can.
So instead of doing all that, you can just do like upper, lower. and
It's the
divide.
same thing,
Okay.
yeah. Because if you think about it, when you do the upper sum, is it upper and lower? I think it's left and right. It's left and right divided by 2.
Left and right.
It's left and right divided by 2. Yeah, because the left sum gives you all the left-hand sides, the right sum gives you all the right-hand sides, and then you're dividing by 2, that's your half that goes out front, right? So it's left plus, it's half of the left plus right. All right, so I have a little visual demonstration. Okay, that looks pretty good. So what we have here, this is the graph of y equals x squared plus 1 from 0 to 2, using the area, finding the area with 2 right-handed rectangles. All right? Would you say that this is a fairly decent approximation for the area under this curve?
No.
No. Is there a way, with still using right-handed rectangles, how could we make it a better approximation?
Change the y interval.
You can't change the y-interval, it is what it is, it's the function.
Change the width of the rectangle.
Change the width of the rectangles, could we add more rectangles in there? Like that?
Yeah.
Does that make it a little better?
Yeah.
Yeah, because
Like-
actually what we've done now is we've subtracted out that space and that space, right?
Put a really big number, put
What's
like
that even
So-
more?
20.
How about, here, let's start with 10 first. Is 10 better?
Yeah.
Is it exact?
No.
No. You wanna try 20?
Yeah.
It's 20.
let's do
Ooh, that's
100.
looking pretty good. I like it. Is that exact?
Do something huge. Do 100.
Let's do 200.
Oh,
Whoa.
that's
Let's go even
exact.
bigger.
Whoa.
Two. Just add another zero.
250.
Add another zero. That's
Okay.
perfect.
How could I get exact area using right-handed rectangles? How many would I use? Yes. How about if I take the limit as the number of rectangles approaches infinity, right? Okay, funny that we should think of that because we know a formula to add together a bunch of stuff and take the limit as the number n goes to infinity. That's what you did on Tuesday. So I'm gonna go back to 4 though and I'm gonna walk you through something.
Can you put in infinity into the?
No, you can't put an infinity in there. Alright. The formula for exact area under a curve actually uses right-handed rectangles. So we're going to derive the formula and I want to walk you through a little bit of how this works. The way that the formula works, I'm going to write the formula up here and then I'm going to explain it with the picture. So we're going to have area equals, and it's going to be, remember that we want, well, let's go ahead and just write it. The limit as n approaches infinity of the sum as I goes from 1 to n. I'm going to write it in words, not symbols, and then I can show you symbols if you want to know symbols. But each rectangle is width times a height. The height is plugging into the function. So it's the left endpoint plus the width times I. So here's what this means. What on earth does this mean? And don't worry, we'll turn off the projection in a minute and you can write it down better. But if you just ignore this and just look at this part, this is width times f of something. So that's width times height. Alright, so you've got width times height, that's the area of one rectangle. Now how do we determine the height? The problem is every height is different, right? So how do you figure out what the values are? Well, we have to plug something into a function. How do we know what to plug in? Well, if we're using right-handed rectangles, we start at our left endpoint. If we added one width and plugged it into the function, we get that. If we start at the left endpoint and add two widths, then plugged that into the function, we'd be there. If we start at the left endpoint and add 1, 2, 3 widths and plug that into the function, we get that value, right? And you start at the left endpoint, add 1, 2, 3, 4 widths and plug into the function, you get that value. So what they're doing is they're saying, hey, take the left endpoint plus and then multiply I, remember I is just a counter, right? 1 width plus 2 widths plus 3 widths plus 4 widths, right? And you're just going all the way until you hit n, whatever n is. So that's how you get, these are all your different, this is the formula to get your different heights. You have to plug this into your function, times your width, add them all together. There's the sum of all the rectangles. So if I didn't have this, that would be the formula for our right-handed rectangle approximation. Now if we want exact area, we add that, and we've got exact area. Does that make sense? So let's turn off the projection.
Can you teach us that the what's it called? The equation for the midpoint that was in the book, or do we not need to know that?
You don't need to know that.
Okay. I was trying to figure that out. It's confusing.
Yeah, it's very confusing. Okay, if you want this with variables, with letters, the formula would look like this. I've always just memorized this, and I'm going to show you a little trick for learning it. But if you want it to look more like a formula, your width is still b minus a over n. F of a plus b minus a over n times I. So if you want it to look like a formula, that's the formula. This is how I have always processed it in my brain. Now, how do I remember the formula? The limit as n approaches infinity, I just memorize. Sum as I goes from 1 to n, I memorize. Of width times f of, there's a rhythm. Left endpoint plus width times I. It's just like f prime g plus f g prime, right? It's the same rhythm. So if you say to yourself, left endpoint plus width times I, left endpoint plus width
Can we
times
do
I,
a chant?
right? Everybody say it. Left endpoint plus width times I. Left endpoint plus width times I. Everybody. Left endpoint plus width times I, right? You have to, once you kind of get that, that's the only part of the formula that gets confusing. Everything else just times the width, right? Plug it in the function times the width, limit of the sum of that. Okay, so let's do a problem.
So since the width is a constant,
Yes, the width is
bring
a
it
constant.
up to the front.
Yes.
Alright.
Okay, bounded by.
Your brother? He got ejected from his match yesterday.
Alright, we're going to find the area of the region bounded by y equals 4 minus x squared and the x-axis from x equals negative 2 to x equals 2. The first thing you do, no matter what, is you find the width. Width is still b minus a over n. So tell me your b minus a.
2 minus
2 minus, negative 2. Do we know n? They didn't tell us an n. Why didn't they tell us an n?
2. That's going to infinity.
Because n is approaching infinity, right? So for these problems, n stays n. So your width is just going to be 4 over n. N stays n on exact area problems.
So you can't-
That means no calculator.
Right.
So you can't like assume that it's going to be like 0 because that was with no problem.
No, don't make n 0. Make n n. And actually, n isn't the width of the rectangle, it's the number of
Well,
rectangles.
I was saying like you can't like plug in infinity and then assume the answer.
Oh, no. But as at the limit as n approaches infinity makes the whole width go to 0, right? Approach 0. Okay. All right, so we've got our width. Let's go ahead and write out our area formula. And there's a little trick with this that a lot of students get confused on, so walk with me carefully. Yeah. Okay, so the first part is the same for every single problem. You write the limit as n approaches infinity of the sum as I goes from 1 to n. Now we have to start filling in stuff. So what's our width for this problem? 4 over n. Here's the part that people mess up. What goes in here is not left endpoint plus width times I.
It's a function of it.
It's f of left endpoint plus width times I. So what you want to do is write your function. Our function is 4 minus x squared do 4 minus parentheses squared. Put parentheses in for your x's. Remember when we had to do f of x plus h and I said put parentheses where your x's are and then you can plug in the x plus h's?
Yeah.
Same thing here. So wherever you have 4 minus variable squared, put a parenthesis for your variable. And in here is where you're going to do left endpoint. What's our left endpoint?
Negative
2
2.
plus width times I. Okay, f of left endpoint plus width times I.
We should move the form.
Now, when you have to actually evaluate this, the first thing you want to do, if you guys remember when we did these on Tuesday and Wednesday, is when you have a sum, you can take this 4 over n, you can treat it as a constant and put it in front of the sigma. So we put the 4 over n here.
And then we split them up, right?
What we have to do before we split anything up is we need to clean this up. So I'm going to go ahead and FOIL out this thing. So we get 4 minus 8i over n minus 8i over n is minus 16i over n plus 16i squared over n squared. So just FOILed. Alright, I'm just going to combine like terms. So 4 minus 4 is gone. Negative negative is positive 16i over n, and then minus 16i squared over n squared.
Would it be minus 8i over n?
You have to do it twice. When
Oh, okay, yeah.
do you understand why?
Yeah.
Because you have an outer and an inner?
Yeah.
Okay. Alright. Are y'all with me?
Yes.
Oh,
Yeah.
good.
Not with her, you're against her.
Okay. Okay. What we have to do now is split up the sum and put the constants in front of each individual term. So we have the limit as n approaches infinity of 4 over n, bless you, times. So now we're going to do the sum of this and the sum of this. This 16 over n goes in front of its sum, which is just I. And then the 16 over n squared, which is negative, goes in front of the sum of I squared. Now we get to use our formulas. Right? Aren't we glad that we memorized them?
Yeah.
So we have the limit as n approaches infinity of 4 over n times 16 over n times, what's the sum as I goes from 1 to n of I?
N times n plus 1 over 2.
Beautiful. Who was the mathematician who came up with that?
Some
Gauss.
weird-
Gauss.
Gauss. Very good. Okay. Sum of I squared, anyone remember?
It's like n times n plus 1 times 2n plus 1 over 6.
Oh, that's so beautiful.
Try my best. Yeah, this is way too long. Can we just not do this?
I agree.
How about
Okay, we're
instead,
done. We're ready to write the answer.
can our final just be learning how to bake cakes? Like master choo-choo train cakes?
We'll talk about that in a minute.
Much more practical.
All right.
Actually, yeah. Much more.
When we do a limit as n approaches infinity, hey, okay.
Sorry. You're not on the form
All right, thank you.
for media release. Can't
That's
be
for
in here.
Sydney. Remember, when we do limit as n approaches infinity, we're just talking about horizontal asymptote rules. I'm going to just think of this 4 over n as kind of a part of this whole big term here. So I have an n squared on top and an n squared on the bottom. So my leading coefficient is 4 times 16, or 64, over 2. And believe me, if you wanna multiply it in, that's completely fine.
Wait, but you wouldn't do anything with
Wouldn't
Now
that
I'm
be
gonna do
n?
4 over n times this way.
but I'm saying like for the, you cancel out the n squared,
Mhm.
but then what about the other n?
These are horizontal asymptote rules. If the degree of the top and bottom
Oh,
are the
yeah,
same, it's
okay,
the quotient of the leading coefficients, right? So here, we have an n cubed on top, and we have an n cubed on the bottom. So our leading coefficient is 4 times 16 times 2. Coefficient of all the n's. So it's 64 times 2, 128
Over 6.
over 6.
And that equals.
This
something.
equals 32 thirds, because I'm so amazing with my math, or 10 and 2/3.
That was a lot of writing.
It's a lot of writing for one problem. Now you have 4 of these to do tonight. Some are easier than others. Tomorrow